These are the 5 basic equations of motion that physics and engineering students will find in their textbooks. They describe motion in a straight line under uniform, constant acceleration. They can all be derived from a simple diagram that I'll explain fully. This diagram, called a VT diagram, and these equations we derive from it are fundamental building blocks of classical mechanics. In this video, I'll provide some sample problems that we'll be able to solve with these equations. I'll describe each variable used in the equations. I'll show how the variables relate to each other on the VT diagram. I'll derive the equations from the VT diagram using geometry and algebra. Then we'll solve the sample problems. Here are the kinds of problems these equations help us solve. If a particle starts moving along a straight line with initial velocity of 1 meter per second, and its velocity increases smoothly over 4 seconds to a final velocity of 3 meters per second, how far does the particle travel during those 4 seconds? We use the word particle to mean an imaginary point-sized object. Since it doesn't have any dimensions, we don't have to worry about measuring from its front edge, back edge, or middle. It's just a particle, so they're all the same. Another example. What constant acceleration is required to displace a particle starting at rest 200 meters in 7.25 seconds? The equations of motion can be used to answer these questions and others like them. The equations reference only 5 variables, which I've color-coded in the left panel. If you've seen any of my other videos, you know I like to color-code things. We'll start with the red S, which denotes displacement. Displacement is the net distance from the initial position. Please note, this isn't necessarily the total distance traveled. If a particle moves 100 meters along a path and then 75 meters back towards its starting point, its displacement is 25 meters, even though the total distance traveled is 175 meters. So displacement and distance are not the same thing. Displacement is a vector having a magnitude and a specific direction. Distance is a scalar having a magnitude but no specific direction. The standard unit of measure for displacement is meters. Please take care and don't be confused. The symbol for displacement is S, which I'm color-coding as red. The unit of measure for time that we'll get to next is seconds, whose abbreviation is also S. You might also see displacement represented by the more reasonable-seeming d. This is usually reserved for first-year or elementary non-calculus environments, since the letter d already has an important job in calculus. Blue t is time, or elapsed time, how long the motion occurs. It's a scalar quantity whose standard unit of measure is the second, s. Initial velocity is denoted by u, which I'm color-coding pale green. Since it's common for velocity to change during an interval of time, there are separate variables for initial and final velocity. Velocity in general is the rate at which displacement changes, so initial velocity is the initial rate of change. Initial velocity can also be abbreviated as v sub I or v sub 0. The I means initial, and the 0 means velocity at time 0, which is the beginning of the problem. Velocity's standard unit of measure is meters per second. Since velocity is the rate of change of the displacement, you can think of velocity as change in displacement divided by the change in time, delta s over delta t. If you're already familiar with calculus, you might recognize this limit as delta t approaches 0 as ds by dt, the derivative of displacement, s, with respect to time. The d's in the derivative are why s is used instead of d to represent displacement. If you're not familiar with calculus yet, don't worry, you don't need calculus to understand or derive these equations. Final velocity is v in darker green. It's easy to remember u and v because u comes before v alphabetically, and the initial velocity happens before the final velocity. Final velocity might also be represented as v sub f. It has the same characteristics as initial velocity, including its standard unit of measure, which is meters per second. Acceleration is pink A. Acceleration is the rate at which velocity changes, and for these equations it's assumed that acceleration is constant. In fact, the condition for these equations to apply is often called UAM, uniformly accelerated motion. Acceleration standard unit of measure is meters per second squared. Acceleration is change in velocity over change in time, or delta v over delta t. Since acceleration is constant, there's no need to take a limit, since delta v over delta t will be equal to the derivative dv by dt no matter the size of delta t. So these are the 5 variables referenced in various combinations in the equations of motion. We can see all of them on a simple graph called a VT diagram. A VT diagram is drawn on a set of axes, where the vertical axis denotes velocity and the horizontal axis denotes time. We'll continue to use the standard units of measure, meters and seconds, but the concept will work no matter what units we use. But we always need to take care to use the same units for time on both axes. So if we choose miles per hour for the vertical velocity axis, then we'd choose hours for the horizontal time axis. And clearly the VT stands for velocity time. Let's revisit our first sample problem and plot what we can. A particle starts moving along a straight line with initial velocity of 1 meter per second. Its velocity increases smoothly over 4 seconds to a final velocity of 3 meters per second. What's the particle's displacement after those 4 seconds? Here we're given the initial velocity, whose symbol is pale green u. It's 1 meter per second at time t equals 0, here. We're also given the final velocity at time t equals 4, 3 meters per second, dark green v. The total time again is given as 4 seconds, here. And we're told that velocity increases smoothly. This means that the line between the initial and final velocities on the VT diagram will be straight. Straight lines on a VT diagram are a result of the assumption concerning constant or uniform acceleration. Let's take an important detour and see what this means. In addition to VT diagrams, where we plot velocity as a function of time, there are also AT diagrams, where we plot acceleration as a function of time. Since we're dealing only with uniform or constant acceleration, the AT diagram is just going to be a horizontal line, because the acceleration is the same for all points in time, though it can be positive, 0, or negative. Here, the acceleration is positive. Positive acceleration means increasing velocity, and the velocity line will have a positive slope. In fact, since acceleration is the rate of change of velocity, the slope of the velocity line is the acceleration. One more time because it's so important. The slope of the velocity line is the acceleration, change in velocity divided by change in time. The initial velocity can be positive, 0, or negative, but its slope is always the acceleration. When acceleration is 0, that means there's no change in velocity, and the velocity line is horizontal with slope 0 because acceleration is 0. Since the velocity doesn't change, it's always the same as initial velocity, whether that's positive, 0, or negative. Interestingly, for the case where initial velocity u and acceleration a are both 0, there's no motion at all. There's no initial velocity, and there's no acceleration to ever change the velocity, so the particle never moves. And when the acceleration is negative, the slope of the velocity line is negative. Here's an interesting case when the velocity line crosses the horizontal axis. This could describe the situation where we launch a ball straight up with some initial positive velocity. We'll assume up is the positive direction and down is negative, so acceleration due to gravity is negative. As soon as the ball is launched, its positive upward velocity begins to decrease steadily under the influence of Earth's gravity. The ball is moving upwards, but accelerating downwards because its upward velocity is decreasing. At this point, its velocity is 0. It's at the top of its path, changes direction because the velocity changes from positive to negative, and it falls back towards the ground with increasing negative velocity. There's a lot of information on a VT diagram. Okay, that's the end of our important detour. Let's get back to our problem's VT diagram. In the problem statement, we were given u, v, and t, and we put their labels on the diagram. Now let's find and label a and s. Well, now we know that acceleration is the slope of the green velocity line, which is rise over run. Let's test our knowledge and find its value. We can use the two endpoints and find their rise over run, delta v divided by delta t. The rise, delta v, is the change in velocity, the vertical distance denoted by the white dashed line. Its length is this distance, dark green final velocity v, minus this distance, pale green initial velocity u. So delta v is v minus u. That makes sense. The change in velocity is the final velocity minus the initial velocity. The horizontal run is delta t, this distance. Since we're starting at time t equals 0, delta t is quite often simply t, which is the case here. So the acceleration is quantity v minus u divided by t. We know all three variables, so it's simple to find that the acceleration is 0.5 meters per second squared, the slope of the vt line. Okay, u, v, t, and a all have geometric meanings on the vt diagram. This leaves the displacement, red S. This turns out to be the area under the vt line. When velocity is constant, this is pretty obvious. For example, suppose a particle is moving at a steady velocity of 3 meters per second for 4 seconds. When we multiply these terms, the unit of time, seconds, cancels. This is why we took care to ensure that both axes represented time in the same units. This leaves meters as the only unit of measure remaining for our answer, and when we multiply across, we get 12 meters. Velocity times time equals displacement. And it may be obvious, but the 12 meters correspond to the number of cells when we multiply 3 by 4. This is so elementary that it's probably how you learned what multiplication was. So the key takeaway is that area on a VT diagram corresponds to displacement. And this is true even when the velocity is not constant. In our sample case, it's pretty easy to count the cells. And we can borrow little triangle wedges to complete the last two squares. So we accidentally found the answer to our sample problem. When a particle starts moving along a straight line at 1 meter per second, and in 4 seconds accelerates smoothly to 3 meters per second, the particle's displacement is 8 meters, because the area under the VT diagram is 8 meters. So now we know how all 5 variables are represented on the VT diagram. With this diagram, a little geometry, and a little algebra, we can derive the 5 equations of motion. They each contain 4 of the 5 variables, which means 2 things. Each can be written 4 ways, each isolating a different variable. If you know any 3 variables, you can use the equations to find the other 2. Let me show the first bullet by writing the first equation, v equals u plus at, differently, so that each variable in turn is isolated on the left side of the equal sign. Subtract at from both sides and we get u equals v minus at. From this equation, subtract v from both sides and divide by negative t to get a equals v minus u divided by t. Hey, this version is the definition of acceleration, delta v over delta t. And from here, to both sides multiply by t and divide by a to get t equals v minus u over a. We just rewrote equation number 1 4 ways, isolating each of its 4 variables. Don't memorize these. When you know the first, you can get them all. If you know 3 variables, you can get the 4th by isolating the unknown variable and plugging in the values you know. The forms in the left panel are the most common way the equations are referenced, and the ones you'll most likely encounter in textbooks or other videos. I'll derive equation number 1 2 ways. First, based on the definition of acceleration, then using the VT diagram. A equals delta v over delta t, change in velocity over change in time. This turns out to be v minus u over t. Multiply both sides by t, and then add u to both sides to get v equals u plus at, which is equation number 1. Now let's look at the diagram and construct the same equation. which is for final velocity v here. It's this distance, u, the initial velocity, plus this distance, delta v, the change in velocity. Earlier we noted that change in velocity was v minus u, but since we're trying to write an equation for v, we can't use v in its own definition. V equals u plus white, and we need an expression for white that doesn't include v. Let's look at the small triangle that denotes the acceleration, the slope of the velocity line. It's similar to this larger triangle because their angles are equal. You might remember that corresponding sides of similar triangles are proportion. Let's note that the length of the bottom side is t. Then we can set up our ratios. Delta v is to a, as t is to 1. Multiply both sides by a, and we get delta v equals at. So from the graph, we get v equals u plus at, same as before, but this time from the diagram. And that's equation number 1. Now, for the second equation, it'll help to remember that we showed this length is at, so I'll label it. Equation 2 is an equation for red s, the displacement, which is the red area under the velocity line. One way to look at this area is as a combination of this rectangle at the bottom plus this triangle on top. The area of the rectangle is its height times its width. The height is u, and the width is t, so ut. The area of the triangle is 1/2 its width times the height. The width is t, the same width as the rectangle, and the height is at, so 1/2 t times at. Gathering our terms, the area of the triangle equals 1/2 at squared. So the displacement, the red area under the velocity line, is the area of rectangle plus triangle, ut plus 1/2 at squared, and that's equation number 2. Equation 3 is another equation that isolates s. To derive this one, we need to focus on this shape. In American English, this is a trapezoid because it has a pair of parallel sides. But to British, Indian, and Australian English speakers, this is a trapezium for the same reason. Regardless, the area of this shape is 1/2 the sum of the two parallel sides times the distance between them. We know all three of these values, so we get s equals u plus v over 2 times t, and that's equation number 3. But let's take one more step and examine this equation. What is u plus v over 2? When we add two numbers and divide by 2, the result is their average. U plus v over 2 is the average velocity, and the average velocity times time is the total displacement. Let's look at the graph again and borrow this triangle and put it here. This gives us a rectangle whose area is the height, u plus v over 2, the average velocity, times the width, t. That's how I think of equation number 3. Displacement equals average velocity times time. For equation 4, it will help to point out something. I said that each of the 5 equations of motion includes 4 of the 5 variables on the VT diagram. Well, each equation leaves out a different variable. Please notice that equation 1 does not include s, but the other 4 do. Equation 2 does not include v, but the other 4 do. Equation 3 does not include a, equation 4 does not include t, and equation 5 does not include u. This way, there's always an equation that includes the 3 variables you know, plus the variable you're seeking to find. For equation 4, we're going to start with equation 3 and use a substitution to remove the t term to give us an equation that doesn't reference variable t. Since the equation is for s, we cannot use s in our substitution. So since equation 1 doesn't include s, we can rewrite equation 1 to isolate t. Actually, when I said that each equation could be written 4 ways to isolate each of its variables, we used equation 1 as the example, and we've already done this. T equals v minus u over a. So when we substitute this in for t in equation 3, we get s equals u plus v over 2 times v minus u over a. I'll rewrite this a bit to show that the numerators are the product of 2 conjugates. I don't have a video on conjugate pairs exactly, but one of my trigonometry videos covers it if you're interested. TR-35, linked in the description. The product of two conjugates is always the difference between their squares. So v plus u times v minus u is always v squared minus u squared. So our equation becomes s equals v squared minus u squared divided by 2a. The most common form of this equation isolates v squared, so v squared equals u squared plus 2as. And that's equation number 4. That leaves equation 5, which is very similar to number 3. For number 3, we took the small rectangle, u times t, and added the triangle, 1/2 at squared. For equation 5, we're going to start with this larger rectangle, whose area is v times t, and subtract this triangle, whose area is the same as this triangle, 1/2 at squared. So, s equals vt minus 1/2 at squared, and that's the fifth equation. You can see how similar equations 3 and 5 are. Small or big rectangle, ut or vt, plus or minus the triangle, 1/2 at squared. The equations are useful and we'll use them to solve a few sample problems, but I consider the vt diagram to be just as important. It's so interesting and useful that these 5 motion variables can have their relationships depicted so clearly on a simple diagram. Here's a grid showing the 5 equations and the variables referenced by each. As I stated earlier, each equation leaves out a different variable, which you can see by the light gray box. I'll show how to decide which equation is best for solving a particular problem by using the first sample problem. A particle starts at 1 meter per second and accelerates smoothly to 3 meters per second in 4 seconds. What is its displacement? There are 2 ways to identify the equation to use to solve a particular problem, and they both really do the same thing. The first method is to circle the variables you're given. There will usually be 3. We were given initial velocity u, 1 meter per second, time t, 4 seconds, and final velocity v, 3 meters per second. Then also circle the variable you want to find, in this case displacement s. One row will have 4 circles. That's the equation to use. The other method is really the same thing, just look at the problem statement and identify the variable not mentioned. In this case, since u, t, v, and s are all referenced, it's acceleration a that isn't, so use the equation that doesn't reference a. Once you identify the equation, rewrite it to isolate the variable you want to find. Let's solve the first sample problem. The first time we actually solved it without using any equations directly. We just counted 8 boxes since the area on a VT diagram corresponds to distance. That was a nice win for the VT diagram. Our equation is number 3. S is already isolated, so we can plug in our values. I'll do the work over here. Displacement S equals 1 meter per second plus 3 meters per second divided by 2. That's 2 meters per second. Times t equals 4 seconds is 8 meters. The same answer we got when we counted the boxes on the VT diagram. I gave another sample problem we'd be able to solve at the beginning of the video. What constant acceleration is required to push a particle starting at rest a distance of 200 meters in 7.25 seconds? We're given u, s, and t, and asked to find a, so the variable not mentioned is v. So we'll use this equation, number 2. You can plug in the values you know and then solve for a, or just rewrite the equation to isolate a on one side of the equal sign by itself. We'll just rewrite the equation from the start. Subtract ut from both sides, multiply by 2 to get rid of the 1/2, and divide through by t squared. We get a equals 2 times s minus ut all over t squared. The math is straightforward, and because the particle started at rest, the ut term goes to 0, since u is 0. So a constant acceleration of 7.61 meters per second squared is needed to move a particle at rest 200 meters in 7.25 seconds. Let's go a step further and find the fifth variable. What will the velocity be in 7.25 seconds? That is, final velocity v. Well, we know every variable except v, so we can really use any equation that includes v, and the first looks as simple as any. v equals u plus at. u is 0, so the final velocity is at, 7.61 meters per second squared, times 7.25 seconds, equals 55.17 meters per second. The analysis of motion in a straight line under constant acceleration is a fundamental building block to more advanced physics and engineering. The equations of motion are all born from the VT diagram, and now I hope you have a greater understanding of it and appreciation for it. I'm Dennis Davis. Thanks for watching, and good luck with your studies. It is hot in Texas.